All right. So normally we would start this thing from the beginning, where I would give you an overview of a cellular telecommunication system, uh, and so on. We may do that a little bit later, and then we're supposed to have a course outline, um, which is in some of the documents that I will be giving you later on. I'll actually direct you to a Google Drive where you can download them or read them on there. Um, so there will be a course outline there where there will be the first part of the course is signal analysis, and then the second part is this part that is called modulation. And in modulation, we have um, amplitude modulation, and we also have frequency modulation. And then we will deal with what happens to these modulation systems when you meet one of the problems that every communication system has, and that is the phenomenon of noise in transmission systems. Actually, I think even in all measurement systems there will be noise, but in communication systems there's noise that is in the transmission medium. There's noise in the components that are used for uh, processing the signals, and so on. So we will deal with what happens to a transmission system when there is when there is noise. So for now, I want to start. This is one part of the course, which is called modulation, and so we'll just dive right in. After covering a few lectures, I'll have to go back to the signal analysis part. But for the time being, this is where we're going to start. And so we'll say that modulation is the process of varying, or if you like, modifying one of the characteristics of a high frequency signal in accordance with the instantaneous values of an information signal. So what are we saying? What we are saying is that there is something we call a signal, which comes from a source. And for example, if we have this thing that we are calling a carrier, which is a high frequency signal, and the high frequency signal will have a frequency, an amplitude, and a phase. So you can see here we have an amplitude, which is the maximum value of this signal, and then the frequency, and a phase. And mathematically, you can express a signal as a carrier times cosine. You could use a sine wave, or you could use complex exponentials. But here is an example of a signal where it's a function of time. A signal is a function of time that carries some useful information. So, for example, if like now I'm talking, if we took a microphone and we put it close to my mouth, then the microphone would pick up the pressure waves that are coming from my speech and convert them into something that is time varying that we can display on an oscilloscope, and that would be called a signal. It's a function of time that carries some useful information. So in this case where we have a carrier that would normally have a constant amplitude. Let me go down a little. Oops, I've gone down too far. Um, let's see. Oops, sorry about that. Hope I've not lost it. It's disappeared. This is very unstable. Okay, I think we are back. Let's see again. Okay, so what we are saying is that tell me if you can't see. Are you able to see? Anybody?
Yes, we can see.
All right. So put where my cursor is, there is what we are calling a carrier. So the carrier, if it is not um, in the form in which we get it, it's just a sine wave. We call it a sine wave, even though we express it as a cosine, and it's just going up and down. And you can see it goes as far to the top and as far to the bottom, and then it goes back. So if it is not modulated, in other words, if we have not changed its amplitude, we have not changed its phase, we have not changed its frequency, then it is just something that goes up and down, like a pendulum that is swinging left, right, left, right, left, right. That is an unmodulated carrier. But if it is modulated, for example, if we have its amplitude modulated, then you would have something like what we are seeing here, where it is large. The excursions are big in some parts and are small in the other. So it's got an amplitude that is uh, going up and down in sympathy with the uh, with modulating signal. So if the modulating signal is like what we have here, which is much smaller, lower frequency, which we might call the message. I will apologize for the the titles that we've got here. I think this message signal I should have put on top so that it is clear. I am not saying that the so-called angle modulation refers to this. This is the message, what we might call the message signal. So if you are speaking and the signal that's coming from your voice is this one, then and the carrier is that, then depending on what you're using, if you're using amplitude modulation, the amplitude modulated signal will look like the guy on top here, and the frequency modulation will look like the one at the bottom. I'll explain what is happening shortly, and then the phase modulation will look like the one before it. What is happening with the amplitude modulation, I think I've already explained. In other words, the amplitude will be high when the signal is high, and low when the signal is low. Then if you have a frequency modulation, which is at the bottom, then the frequencies, in other words, the number of times the signal goes up and down will be higher when the signal has got a high amplitude, and will be lower when the signal has got a low amplitude. So when the amplitude is low, then it is vibrating less, and when the signal has got a high amplitude, then the vibrations will be faster. So you have, oh, somebody's telling me that my cursor is not visible. So this is going to be tricky. All right, so then I'll have to talk differently. That's interesting. The cursor is not visible. So let's see. And I can't highlight anything. All right. So, but you can see the diagram where one is written linear modulation. You can unmute your mic and answer.
Yeah. Yes, we
Joseph?
can see. Yeah.
All right. So I'll bear that in mind. And so what then we're saying is that where it says linear modulation, that and then in brackets amplitude modulation, then that the figure that is to the left of that text is showing what happens when you have amplitude modulation. The the figure that is the sketch that is below that is just a line that's going up and down where it says angle modulation, but there is below that something with an arrow pointing to a message. That is the message, the one that seems to be of a lower frequency, that is going up and down, two troughs down and maybe three peaks up. That is the message. We say that is a lower frequency signal. Then third in that list is the carrier, and the carrier, as you can see, it just looks like it's everything is sort of uniform. the number of times it's up is the same as the number of times it's down, and it goes as far up in every cycle. There are many cycles there. In every cycle, it goes as far up as it does down, and without much more variation. And then, so that is the carrier, which when it's amplitude modulated, you see what you have on top there. Then number 4 is phase modulation, and in phase modulation, it is very usually we prefer to talk about frequency modulation, and then we'll say that there is a relationship between the phase modulation and frequency modulation. So I'll do that here, and say that at the very bottom you have our message signal shown in there, and we are showing that where the message signal has got its lowest value, the carrier has got uh, fewer excursions. You can see that the cycles are more visible. You can see them. They are not as dense when the signal is low, and in parts where the signal is high, there are more cycles, to the extent that the thing is almost becoming dark. So if you like, the gray shading is darker where the signal is strong, and it's lighter when the signal is weak. That is frequency modulation. The relationship between frequency modulation is such that one is sort of like the derivative of the other. And in this diagram, if you were to take the phase difference between a frequency modulated signal and a phase modulated signal, you will find that one is just the other one shifted by 90 degrees. So the same phenomenon that we were giving, instead of talking about the signal being low to have fewer excursions, now you'll be looking at the point where the signal is steep. If the signal is steep with a positive, if the slope, let me put it this way, if the slope of the signal is positive, then what you see is dense, and when the slope is negative, then the output is like fewer excursions. So it's, instead of dealing with the signal itself in phase modulation, you actually have the derivative that's at play. So that's just an example of what happens to motivate where we are going. But otherwise, we will start with this idea of frequency translation. Because when you may then be wondering why do modulation? We just started off here by saying modulation. You have a signal that comes from a carrier. You have a carrier that comes from some source, and you would like to use it for communication, and or better yet, you have a signal that comes from a source, like somebody's voice, and you would like to transmit this over the air or through some copper wire or coaxial cable, and so on. And the question then is, why don't you just have a microphone, then convert the signal from the speaker into some voltage wave, and then transmit it? Why frequency translation? In other words, why do you involve this carrier in it? When you involve a carrier in here, like we were doing, we are said to be doing some carrier modulation by the signal. So what we do here is that in combining the signal from the source with a carrier, we are said to be doing frequency translation. And frequency translation, and as far as this part of the course is concerned, is equivalent to modulation. We'll see that shortly. So we're saying frequency translation. The text there is saying that sometimes frequency translation is referred to as modulation. although modulation is much broader than just translating frequency. And I think for the moment we have not said what is this frequency translation that we're talking about. We'll see that how it's done in a few minutes. All right. It's advantageous and convenient in processing a signal in a communication system to translate the signal from one region of the frequency domain to another. One of the reasons why you may want to do this thing called frequency translation is that you would like to do frequency multiplexing. What does that mean? What that means is that if you have several, let's say, stations, radio stations, when you go to their studios, the signals that you meet are in the same frequency range. If they're playing some music or people are giving a speech or whatnot, all those signals will form one frequency range. The voice frequencies go from about 20 hertz, not zero, from 20 hertz to 20, should we say 20, to 3.4 kilohertz. That's the voice. And then if you have music in it, the music will go from that 20 hertz to 20 kilohertz. So if you are dealing with voice alone, you'll have a frequency range from, let's say, from zero to 3.4 kilohertz, and many people would say it's from 0 to 4 kilohertz. All right. So all of them, a radio station in Machakos, another one in Kisumu, another one in Mombasa, and so on. So if you took their signals and you just sent them out as they are, then they are going to clash out there because they're using the same. It's like everybody trying to speak at the same time, and then the people who are trying to receive the transmissions will be confused. There will be no way of telling one station from another. So what you do is you ensure that every station is given a specific frequency range, so that when somebody wants to listen or see whatever they are transmitting, then they just set their receiver to the frequency range by selecting a carrier. So one of the reasons for frequency translation is that we ought to be able to see who is to see or hear transmissions from different sources, and that's basically frequency multiplexing. And then there is a very important item here, which is necessary whether or not there are others also transmitting their signals. And this thing is the idea of the practicality of transmitting antennas. So there's practicality of transmitting antennas, then there's a concept of narrow banding, and then there's common processing. I'm going to go through them one by one. I've already done frequency multiplexing, and now we'll go to the practicality of these antennas. The antennas, when you use them to transmit signals, they are most efficient when their wavelength, the wavelength of the antenna, is close to the frequency, or better yet, you can say that the signals are transmitted most efficiently when their frequency is close to the order of a wavelength. Usually, we choose the antenna length to be once we know the frequency, we can calculate the wavelength, and the wavelength is lambda. And you can choose, if you choose lambda from a quarter, if you choose the length of the antenna from a quarter of the lambda is the wavelength, to about a half, we are saying it's of the order of the wavelength. The frequency of what you are transmitting will give you a wavelength where the relation f lambda equals c. I hope that from the EM field theory, you actually from the wave itself, the wave from the discussion on waves, you know that F lambda equals C. So the frequency times the wavelength equals the speed of the waves in the medium. And we are assuming that the media that we use are such that the frequency, the speed is more or less the same as what we have in free space. Whether you use copper or use coaxial cable or you use free air and so forth, it doesn't vary very much from 3 times 10 to the 8 meters per second. So if you use that, then you can say that if you are given a frequency, you can get the wavelength by dividing the speed by the frequency. And so if you want to have an antenna that is of the order of a wavelength, maybe a quarter of a wavelength or a half a wavelength, we'll just say the order of a wavelength, then you would take the frequency that you got, and so we take the speed and divide by the frequency. And so we are having a signal, an example here, that if you have a signal of 1 kilohertz, maybe an audio tone, and then you want to find out what the wavelength is of that. It's going to be 300 kilometers. So what you do is you take the speed of light and you divide by 1 kilohertz, and you're going to find that it is 3 times 10 to the 5 meters, which is 300 kilometers. So already you're trying to build an antenna that is of length 300 kilometers. Obviously, this is not practical. You're not going to find where to put this kind of antenna unless several countries have come together and they have agreed that they are going to put together a section of their territory to allow that kind of distance to be used. If the need is there, it can be done. And there are some worldwide projects where there are some installations where the antenna lengths are very very large, but that's another side. That's now answering a different question. We were talking about trying to implement something that somebody can tune in the comfort of where they are. Then this is impractical. 300 kilometers you cannot build. So what do? You still want to transmit this audio tone that is coming from somebody speaking. So what you do is you can translate the frequency to by let's say having a carrier of 1 megahertz, and then you're going to get an antenna of 75 meters. That is still impractical, but at least it's now small enough to fit in the premises of somebody. The person transmitting can build something like that. That is still impractical. However, you can push it. Let's say you use 1 gigahertz. Yeah, 1 gigahertz now will bring actually maybe 100 megahertz will be better. It will be 0.75 meters. That will be much better. So you get the idea that if you have a higher frequency and you are able to translate that 1 kilohertz to a higher frequency, then the antenna length is going to be small enough so that somebody can construct it and sell it to another one to implement. So what we are saying then is that the wavelength may be reduced to the point of practicality by translating the signal frequency to a higher value. That's the point of this. Right. So in other words, the practicality of antennas, the antennas are used for both transmission and reception. And so what's happening is that you need the frequency to be in the right range for the antenna length to be practical. Then there's this other thing of narrow banding, and I think we didn't have, some of these things that we meet are a consequence of historical accidents, I think people would be working and they use, let's say, the first term that comes to mind, and afterwards, when you analyze it, you find that they could have used something better. This is one of them. The idea of narrow banding, it does not mean that we are changing something that was of a wider band to something that is that has got a band that is smaller in width. In other words, if you are taking a signal that goes from 0 to 4 kilohertz, when in the context of this so-called narrow banding, we don't mean that we are going to squeeze it down to maybe to 1 kilohertz or 200 hertz. No. What we mean here is that we are bearing in mind that when you are transmitting, the antenna wavelengths are the antenna lengths are of the order of a wavelength. And so you'll be saying that if you have a signal that goes from 50 hertz to 10 kilohertz, so then you'll be trying to say, if I'm to transmit that antenna, then an antenna that is tuned to 50 hertz would have one value, would have one length. You take the C and you divide by this, and then the one that is tuned to the top end, which is 10 kilohertz, will have another value. So when you're taking the ratio of the antenna requirements from one end to the other, you'll find that the ratio is 200. In other words, the ratio of the high frequency to the lower frequency is 200. So at the higher frequency, you're going to have a small antenna, and at the lower frequency, you're going to have a large antenna, and the ratio of the two is actually just the ratio of those two numbers, and you get that you need an antenna that is 200 times at one end than its value on the other end. But how do you do that? You want to be able to transmit and receive this signal with one antenna. And this is telling you that one end, one antenna, the other end, 200 times, it's not doable. So what you'd like to do is to use frequency translation so that it appears, when you look at this thing from one end to the other, it appears as if it's just one. In other words, when you take the ratio of the length at one end and to the length at the other end, then it's going to be just the same. But the ratio of the length is just the inverse ratio of the number of frequencies. So if you translate this 50 hertz to 10 kilohertz by using 1 megahertz, then you're going to have 10 times 10 to the 6 plus 50 to 10 to the 6 plus 10 to the 4. And the ratio of that now is about 1.01. That is doable. In other words, it's possible to use the same antenna at both ends. So what we say here is that the signal has been narrow banded, and that's where I have a quarrel, because it may appear as if our signal, which was going from 50 hertz to 10 kilohertz, a bandwidth of almost 10 kilohertz, 9 kilohertz, I think, and 50. So it's 9050. Yeah, so it's 9.05 kilohertz. That's the bandwidth, and it's still the same bandwidth here. So it's not been the bandwidth has not been changed, but we're saying the signal has been narrow banded because it appears now that's the top range, the top of the range, as a ratio of the bottom. It's just 1.01, so that's okay. So at least you can use the same antenna through the full range. The 0.01 there is not so much of a problem. So what is happening is that wideband and narrowband are being used here to refer to an absolute range of frequencies, not the bandwidth of the signal. The bandwidth has not changed. Okay, you can stop me anywhere if you have a question. Just unmute yourself and speak, so that I don't go on talking and then at the end somebody tells me I did not hear what you are saying. Okay. Why? What's the other reason why you might need frequency translation? It would be now you think about a receiver and of a transmission, and the receiver, um, you wouldn't want a receiver to be shifting itself. If one transmitting station is transmitting at 10 megahertz, or let's say 100 megahertz, another one at uh, uh, 50 megahertz, and so on. You would not want your receiver to be shifting itself. That you move everything to the frequency of the incoming signal. It is better for the receiver to have a part of it that is doing frequency translation, so that what is coming in is translated to a common frequency. So you set the tuner to the frequency of the transmitting station, then it brings the signal to the same level. So if somebody was transmitting at 100 megahertz, you can bring that to 4.5 megahertz. And if somebody was transmitting at 200 megahertz, you can bring that to 4.5 megahertz, so that the processing equipment in the receiver after the frequency translation is the same. In other words, you'd like to have common processing, so signals that are coming from different frequency ranges can be brought into a common range so that they can be processed by a single piece of equipment. That is one. I think we'll leave it like that for now. Later on, when we'll be talking about the demodulation of some signals, we'll see other applications where common processing may be useful. But I think we just want to motivate it this way, that you may have signals that are coming from different sources, frequency ranges, and you'd like to have one common processing that will be that will not need to have its frequency changed from one value to another after the frequency translation has been done. So we basically say that one of the fourth reason for frequency translation is common processing. In other words, you bring everything to a common frequency range, then your same equipment can be used regardless of where the signals are coming from. So how do we do this thing that is called frequency translation? Because we are saying that we want it, and you'd like to be able to do it in the lab. How do you do it? Um, the answer is easy. All that you do is you multiply by a cosine. In other words, you multiply by a sinusoid. Sinusoid is another name for a signal that is of the form is either a cosine of some constant times time, or a sine. The difference between a cosine and a sine in terms of these signals is just that one is 90 degrees uh, behind the other. And so, in other words, for example, the cosine has got its peak at 0, and the sine will reach its peak a quarter of a cycle later. So you can say that the sine is 90 degrees behind the cosine, with a quarter of a cycle is a quarter of 360, and that's 90 degrees. Okay, so if you have a message signal m of t, which has got its amplitude am, and it's got a frequency fm. So fm is the same as omega m is the circular, so not circular, the angular frequency, and it's the same as 2 pi f. So fm is the frequency. So you have a signal that has got a frequency fm, and amplitude AM, then you can write it like that. That M of t is AM times the cosine of 2 pi Fm of t. So we're saying AM is the constant amplitude, Fm is omega m over 2 pi is the frequency. And if you wanted to look at this m of t that we've got here in frequency, in other words, you'll be saying in terms of the frequency, then you can see that below in the figure below, I think somebody told me that my cursor is not visible. We'll have a different way of sharing my screen so that the cursor can be visible. I am sharing from the Google Drive, so it's probably not picking things from my screen, from my keyboard. Okay, so there's a diagram there where we have, I don't know whether you can read, it's saying the amplitude of the spectral component, and the peak there is AM over 2 in the top part of the diagram, and we are having a signal. There's a spike at minus FM and another spike at plus FM, each of amplitude AM over 2. I think later on we'll use. Okay, we can do it here. I hope you are familiar with the way of writing cosines and sines in terms of complex exponentials. I don't know if that needs doing. Let me prepare a handout and then give you later on. But you can write the cosine of theta, let's say, as e to the j theta plus e to minus j theta, and divide all of that by 2. That's called Euler's relation. Euler is spelled Euler, and many people might say Euler. You might have met him in mathematics, and maybe they could have referred to, depending on the speaker. I usually tell people that depending on who introduced something to you, you may find yourself leaning one way or the other. It's read as Euler, just like there's somebody called Neumann, and Neumann is written as Neumann. I think it's double N. And so in their places they say that. But if somebody says Newman or somebody says Euler, Euler, and so forth, so long as we understand what they're saying, we move on. Realize that if you try to quibble on those small things, I just realized that somebody had muted me. Felix. Okay, I'll go on. I hope you are hearing me.
Yes.
If somebody is not hearing, you can hear.
Yes.
Yeah, but I don't know how much you have missed, because I just realized when I checked my mic that I'd been muted. But anyway, it's recorded, so you can play back later on when I give you the link. Okay, so basically what I was saying is that there's a diagram here, and in the diagram we are showing in what you'd see in the frequency domain. In other words, if you looked at our signal m of t in the frequency domain using a spectrum analyzer, that you would see a spike um, at frequency FM. So if FM was 1 kilohertz, you would see a spike there at 1 kilohertz of amplitude AM over 2. So if AM was 10, you would see 10 millivolts, then you see 5 millivolts there. Now, because of that, the relationship, that Euler's relation, in other words, if you take a cosine, cos theta, you'd take cos theta as 1/2 of the sum, e to the j theta plus e to minus j theta. So the minus bit that is in there shows up as a negative component in the frequency domain. So somebody may say, how do we know that? How we know this is that if you did, oh, okay, so it's saying something is back. I don't know what is back. If you did, you took this signal and you did frequency translation with it. In fact, this is the evidence. By multiplying it by a frequency so as to by carrier, so as to get a frequency translation, then you'll find out that there will be two components. So let's say, I think let me just go down in this let's see. So we have our signal m of t, which is am cos 2 pi fmt, and we are trying to multiply. So below the diagram, we are showing the spectral pattern of the product waveform. That is, our m of t has been multiplied by ac cos 2 pi fct. Okay, putting it that putting omega c to be 2 pi fc. When you do that multiplication, you are going to get cos times cos. And the identity is that cos A times cos B is 1/2 the cosine of the sum plus 1/2 the cosine of the difference. So now what do we do? You may be wondering, do we have to memorize all these things? I think what I'll say is that the short answer is no. You don't have to memorize that cos A cos B is 1/2 cos of A plus B plus 1/2 cos of A minus B. You don't have to memorize that. I'll give you those in an exam. I'll give you a list of those. But I just point out that if you after you use these things enough, some of those things will just be etched in your mind. You will just find that you can sing them out without having to be given a table. However, we're not going to force you to get these things from memory. I will give you whatever you need in an exam so that you don't have to put the wrong thing down and then you find that the answer is not coming out right because you used the wrong thing. All right, so I'm saying if you use frequency translation by multiplying the two signals, then what you see in the spectrum analyzer, you would think that the original signal, which had an amplitude of AM, when you translate it to the right by this multiplication, that you are going to get one single frequency component. And you would think that you would get a single frequency component, and the amplitude you think would be a product of the two amplitudes. In other words, the amplitude of the original signal, AM, and times the amplitude of the carrier, AC. That's what you think you'd get. Well, you take a look and you find that it is not one, but there are two. And the amplitudes are not AM times AC, but it is AM times AC over 4. So now you'll be saying, is there something wrong perhaps in the cables that I'm using to make this, to measure these signals, or what is going on? Because what I'm seeing, by the way, even when you are observing the original signal of the spectrum analyzer, you would find that if you measure from the signal source, the signal generator, which you set to give you, for example, 10 millivolts peak to peak. No, not peak to peak. Let's say 20 millivolts peak to peak. That's an amplitude of 10. And then when you look at the spectrum analyzer, the amplitude will be a half, 5 millivolts. That's what you will see. The frequency will be right at 1 kilohertz, let's say, but it will be a half. And then we'll be wondering what is happening to the other half. The other half is hiding behind on the negative side. The answer is the Euler's relation. And now you get the further evidence of that when you do frequency translation, because when you do frequency translation, the whole thing moves, you would think, to the right, but it also moves to the left. And so you'll find that a half goes to the right and a half goes to the left, and there was already a half and a half initially, so this thing is a quarter. So in other words, our original signal that was a frequency FM and amplitude AM. When you do the frequency translation, you are going to get the whole thing centered at the carrier frequency, but to the right of the carrier, you get a quarter of the product AC times AM, and to the left, you get a quarter, and so on. And if you take a quarter plus a quarter, that's only a half. It's not giving you what you would expect. So the other half is hiding on the left. And that is some discovery there. So what you find is that if you use this identity, cos A cos B equals 1/2 cos of A plus B plus 1/2 cos of A minus B, then the product of M of t times SCT is the cosine of the sum plus the cosine of the difference, and that's what's giving rise. So you can see that there's a component of the sum of the frequencies, and there's a component of the negative of the frequencies, and then the whole picture is also shown so that there's a reflection about the vertical axis of the same thing on the negative side. We're doing this thing for the first time, so maybe it's going to be confusing initially, but you see it a few times, it will be easy to follow. So if it's not making much sense for the time being, it's fine. You just read it a few more times, and you'll be okay. So we have that figure 221b. In other words, the one that is below, where there are 4 spectral components. The dashed lines I'm just using to show either the frequencies or the amplitudes. So the horizontal dashed line is to show the amplitude, and the vertical dashed lines is to show the frequency, the carrier frequency. Okay, so we're saying then that the spectral amplitude pattern, by spectral we mean in the frequency domain. So when you look at the spectrum of a signal is its Fourier transform, and that's what you see in the frequency domain. Where do you see that? On the spectrum analyzer, if you are in the lab. All right, now we want to look at what happens when you have a signal that is a little bit more interesting, because what we had there was just one tone in a single frequency that would sound something like this. That's one tone. If you strike a note on the piano keyboard or on the organ keyboard, you'll hear one tone. But the signals that we deal with in real life are not single tones. They could have a continuum of frequencies. And so we are having a diagram here where we are attempting to show something that could be varying. So it looks like we have some inverted M. I don't know whether it's not quite an M, but anyways, that's one thing that we may have. And as a result of frequency translation, you would have a component of that signal on the right, and a component of that signal, a copy of that signal on the right, and a copy on the left. Everything has been multiplied by half. So if you just took cos 2 pi FCT, that's a carrier, and you multiply that by the signal, then the spectrum gets copied, it gets replicated one to the right and one to the left, and the bandwidth is the same. So that's just an example. This kind of multiplication that we are talking about, where you are taking a signal and multiplying by a carrier and so on, sometimes it is called heterodyning, and then the other term is mixing. So you take two signals, and when in modulation language they talk about mixing, then it's basically multiplication. I don't know where. Again, that's another. I shouldn't say I don't know. That's another accident, because you think that when you're mixing, you're adding. But here the mixing is you're mixing signals, so you're multiplying one signal by another. They can argue that you're adding frequencies, adding and subtracting frequencies. So you're mixing in that sense, adding and subtracting. Okay, so mixing and heterodyning. All right, those are new terms there. Then you talk about the components of the spectrum above the carrier frequency are called the upper sideband, and the components below the carrier frequency are called the lower sideband. That's just terminology there. I have put the frequency ranges. So from FC to FC plus FM, that's the upper sideband, and the lower sideband is from FC minus FM to FC. FC is the carrier frequency, and that's the lower sideband. It's that this term lower sideband and upper sideband, I think we need to keep our finger on that for a while, even as we move on, because later on, when we'll be making some observations and trying to think about the most efficient way to use the frequency bandwidth, we will think about having either an upper sideband only transmitted or a lower sideband only transmitted, because we'll be arguing that the information that comes from the message is totally in one sideband. You don't need both sidebands. And so if you want to have an efficient use of the bandwidth, then one half is enough. All right. We'll get to do some calculations a little bit later. For the time being, we're just introducing ourselves to terms. So how do you recover? You remember we did multiplication of a message signal M of t by a carrier, and now you'll be saying, how do I recover my M of t? Because the M of t is the one that is that's the message signal. So you look at what happens here. If you take the same M of t that was multiplied by cos, so I'm looking at equation 2.4, and take the M of t multiplied by cos omega ct, and I multiply again by cos omega ct. So let's say you are the receiver receiving the signal that was multiplied by cos omega ct, and you just get another copy of the carrier, and you do the multiplication. Then you're going to find that now you have M of t multiplied by cos squared omega ct. But there's another identity that cos squared is the same as a half plus a half cos of twice the angle, twice the whatever you have here. Here's omega ct. So when you expand that, then the result of the multiplication is equation 24b, which is mt over 2 plus mt over 2 cos 2 pi, sorry, 2 pi fct, or if you like, 2 omega ct. Then what you'll then say is that the component that is mt over 2 multiplied by cos 2 pi fct is at a higher frequency than m of t. So if you use a low pass filter, you can select MT/2, the lower, the first part. MT/2 can be selected by low pass filter because the other guy, which is MT/2 cos 2 pi FCT or cos 2 omega CT, that will be, we will say that will be sitting at a higher frequency, and a low pass filter will pick up the lower guy. And so it looks like the same circuit, if you like, that was used to generate MT cos omega CT, because you took MT and multiplied by cosine. Now you're taking what has been received and you're multiplying again. So that same circuit can be used to get your signal back, provided that you add a low pass filter. We're moving fast for the moment, but there will be. There's a question that I brought in an exam concerning this. So I think what we'll do is I'll give you that so that you can see how this ties in with some diagrams. Here there are no diagrams because these notes are intended to supplement with what I would be writing on the board. So they are not in the form that is most suited for this kind of presentation, but we are doing what we can under the circumstances. So if it's looking like you're almost falling asleep, bear with us, or we bear with ourselves until things get normalized. All right. So we have modulation again, sort of a repeat. So we say modulation is the process of transferring information signal to a high frequency carrier by modifying a suitable parameter of the carrier. What do we mean? The carrier would have an amplitude like we have down here, S of t, has got an amplitude AC, a frequency FC, and a phase phi. So what will happen is that if you modify the amplitude, then you get an amplitude modulation. You get amplitude modulation, and if you modify the frequency, then you get frequency modulation, and if you modify the phase, then you get phase modulation. So all of them with respect to the carrier. The carrier is written as AC cos 2 pi FCT plus phi. Phi is the phase. The phase is just a measure of the starting point. If you are interested in a book that you can use to read, there's a book by Simon Haykin that's called Communication Systems. All right, so talking about amplitude modulation, and what you will do is have an example. Amplitude modulation, S of t is given as AC 1 plus, there's a parameter Ka m of t, and then the whole thing is cos 2 pi FCT. That is, you can see that the whole thing in square brackets multiplied by AC is the amplitude, and then the carrier part is the cosine. And what then happens is that the result of this is that you have a signal of a particular a fixed frequency, but its amplitude will be getting changed by this m of t, but multiplied by this parameter that's called Ka. So Ka is referred to as the amplitude sensitivity of the system, and it's in units of the inverse volts. In other words, that's supposed to be the whole thing. Ka times m of t is supposed to be dimensionless because the dimension is given by AC here. So that Ka is a parameter of the modulating system, and then AC is the carrier amplitude, FC is the carrier frequency. So with this, I hope I have a diagram that we can see. Yeah. All right. So if you think about what is called single tone amplitude modulation, a single tone will just mean you have one the modulating signal having a specific frequency. M of t. Sorry, f of t. So our Sm of t, I think previously I had used m of t, and I'm using Sm. Need to reconcile. So the modulating signal is Am cos 2 pi Fm of t. That's a single tone, and the carrier is this blue. I hope it's showing on your screens as blue. The carrier is this blue signal, which is of a much higher frequency. You can see the cycles are many as compared to the red one, which is the yes. I think can you speak? Somebody just asked a question there. Just
Yes,
unmute yourself and speak. Yep.
I was asking when
Yeah.
we were doing the retrieving of the signal and then we
Yes.
multiply it by the carrier signal again, wouldn't
Yeah.
the amplitude be halved like it was halved when we were modulating?
Good point. Yeah. It will be half, but what you want is not so much. You can compensate for that. Remember, we're saying that after that multiplication, you're having a low pass filter, right?
Yes.
You're having a low pass filter to knock off the higher frequency part. So you can put a gain of 2 if you like. You can put a gain of 2 in that low pass filter to restore
Oh,
to restore whatever you'll be missing as a result of that recovery. But
oh,
that's a good point. Yeah. Okay. All right. So you have the carrier signal as the blue one, and the the modulating signal is the red one. And we are just remarking, I don't know whether you can see in the blue diagram where at the bottom there I've indicated that the difference between the peaks, in this case the trough, is 1 over Fc. And it's not appearing very clearly there. And likewise in the red diagram, the difference between the troughs, which is the same as the difference between the peaks, is 1 over Fm. Okay, so what happens that when you do the single tone modulation, and you do what we had done previously, in other words, you just multiply in figure 225C. If you multiply the two guys on top, the blue one and the red one, then the output, as you'd see on the oscilloscope, would look like what we have here with the dashed outline in red. That's what you'd see, and that is called a double sideband suppressed carrier signal. Now, what you get as a result of that multiplication, you multiplying the signal in figure 2.5a by the signal in 2.5b, then you get what is in 2.5c, which is a signal that we had previously, the one that we were trying to demodulate by doing a multiplication, and we have just said that the low pass filter will have to be put with a gain of 2 to compensate for whatever we'll be losing as a result of that double multiplication. Okay, so we'll get this signal that is called a double sideband suppressed carrier. The reason why it is so called is that you will find that there are two sidebands there. You indicated what the sidebands are. There's an upper sideband and a lower sideband. The upper sideband will be the components in the frequency domain that are above the carrier, from the carrier and up, and that's the upper. And then from the carrier and below is the lower sideband. This signal has got components on the upper and lower sideband, but there's no component at the carrier. So it's like the carrier has been suppressed in the in the signal. So we're referring to it as double sideband suppressed carrier. And the demodulation that we just described, we'll come back to it later on because it's got a problem that we'll need to address. not just yet. Now we go to 2.5D, which is a multiplication, but we are bearing in mind. Yeah, I think I'm sort of confusing you by introducing too many terms. Earlier on, I had put Ka, and now I'm having Ma. But maybe better you just as well uh, get used to them, because sometimes we use Ma and sometimes we use Ka. And here we have it. We have a parameter which is Ma that is equal to Am Am over Ac, and that's the modulation index. So what you end up having is this. If the labs were going on at the moment, then you would have seen some of these things in the lab. In fact, sometimes in the past when things were normal, I would be covering this when some people had already done these things in the lab, and so it was easier to follow. But right now, uh, we have to rely on this totally. Okay, so when you multiply and you add a carrier, then this is called AM with carrier. This figure 2.5D. It's like a carrier is in there. I don't know whether you can see there's an equation at the bottom um, where we are having S subscript AMT is AC into round square brackets 1 plus MA cos 2 pi FMT, and then you close the square brackets and then a cosine. The one that is inside there in that square bracket, it's like it is AC multiplying cos 2 pi FCT. So there's a carrier in the signal. It's like you have what is appearing in 2.5C, and you're adding a carrier term to it. And so this is called AM with the carrier. And when people talk about AM, this is what the one that we mean. And you keep that in mind. That figure 2.5C, which is the double sideband suppressed carrier, and 2.5D, which is the AM with carrier, sometimes called the conventional AM. When people talk about AM, this is the one that we mean. The reason will become clear shortly, because it solves the problem that we have with the 2.5C. In 2.5C, if you want to use it's a very simple circuit that is called an envelope detector. For it, you find that it won't work, and you can work with the 2.5D. And the circuit is so simple, just three components: a diode, a capacitor, and a resistor, which you can hook up very quickly. And you just need to choose the capacitor to be over the right value, and it works. So, in the desire to use that circuit that I just described, the figure 2.5D is preferred. But the other one has got its simplicity of generation. And so we'll look at ways of dealing with it when the problem that it has occurs a little bit later. All right. So we're just having some expressions there. You can find out the modulation index. Well, let's go back. We have indicated from the peak to peak of the signal in 2.5D, the peak to peak we have indicated as 2A. I hope you can see on the left there. And then from the trough to trough, the bottom there is 2B. And the peaks of the red outline from one to the other is 1 over FM. And from the peaks of the blue ones, 1 over FC. This is a plot in time. So whatever we are measuring horizontally is time, and whatever we're measuring vertically is volts, if the signal was in volts. And if it was current, then of course it would be amps or milliamps. Right. So we are showing how to get the modulation index from that diagram, and we are saying it's 2a minus 2b divided by 2a plus 2b. Now, some people may decide to cancel the twos, but the diagram that we have drawn here is, if you label them, you choose to label them as A and B, where we have 2A, you have A, and where we have B, 2B, you have B. It's fine. But the modulation index is just the ratio of the difference over the sum. It is easier on an oscilloscope to measure from peak to peak, or from trough to trough, the bottom to the bottom. It's easier to measure that than trying to find out where the zero is and saying, yeah, from the zero to the peak is A, and so on. It's easier to measure because the display on the oscilloscope can be moved up or down, but wherever you moved it, you can see where the peaks are. And so we measure peak to peak, 2A, and then from the bottom to bottom, 2B. So this is more of a practical representation rather than anything else. So I've given the two expressions there, where you can get M as 2A minus 2B over 2A plus 2B. And it's putting the same comment here, that in the lab it is easier to measure the values 2A and 2B. And so the modulation index can be found in terms of those two. So then the frequencies you can get from the carrier. One other thing, if you're trying to find the carrier frequency from, let's say, 2.5 D, as I usually ask in many exams, I think it's one thing that I give people so that they can feel confident answering the questions that are to come later. When you want to measure something like 1 over FC, then what you do is to count the peaks. You can go from the beginning to the end and ask yourself, how many peaks are there? From the first peak, you can leave the first peak and then you go 1, because you don't count the first peak. Remember, you're trying to measure time extent. So from the first peak, you go to the next one, that's 1, and so on. If you count that way, you say you get 16 of them, and then the time from that point to the end there perhaps is 10 milliseconds, or 0.1, let's say 10 milliseconds. Then you say 10 milliseconds is the time, and how many cycles have I got? I have got 16. So you're going to say I've got 16 cycles in 10 milliseconds. Then the number of cycles per second is the frequency you want, and there you have it. So if you are trying to measure the frequency, it's better to take a bunch, because measuring from one peak to the other might be hard to see. But if you go on over a longer period, the measurement becomes better. That's a technique that is used in improving the accuracy of measurements. If let's say you are trying to weigh small balls, and instead of weighing one and registering a value, you can take, let's say, 100 of them. If that option is there, you can take 100 of them and you weigh. Then you divide by 100. The resulting accuracy will be improved. If the instrument that you're using to do the measurement was having an error of plus or minus whatever, when you divide by 100, the accuracy will be divided by 100. So I'm just pointing that out. I remember when we were in high school, we were trying to get the width of a bunch of papers using some vernier calipers, and the teacher told us that instead of measuring one, you would take maybe 200 sheets together, and then after you've measured, you get a number and you divide by 200, and the result will be much better than if you try to measure one. So I'm just pointing that out because you are applied scientists, and you need to be sensitive to how to improve the accuracy of measurement. That's one idea that you can apply when the time calls for it. Um, I'll be stopping shortly. These diagrams that we are having here are basically just indicating more of what we have uh, done already. So there's a diagram in figure 2.5e just showing the relationships between the side bands in an amplitude modulated signal. The leftmost part is the signal, and then there's the carrier and the frequency components that are shown there. I think there's no point to beat it. We already have that information there. You'll just be seeing that on the upper sideband, which is on the rightmost part of the diagram. You have something that looks, I think it's orange. It's of a higher frequency than the carrier. I don't know whether that's, yeah, the variations are more. It's a higher frequency. Then the carrier is in some form of bluish green, and uh, before the carrier you have something that's slightly lower, and then you have the message signal on just before the left, and finally at the extreme left you have the amplitude modulated signal, just so that you see them together. All right, so some example here. So we're saying a standard AM broadcast station is allowed to transmit modulating frequencies up to 5 kilohertz. If the AM station is transmitting on a frequency of 980 kilohertz, what are the sideband frequencies and the total bandwidth? Very simple. The modulating frequency is up to 5 kilohertz. What do we mean by the AM station transmitting a frequency 980 with a sideband frequency? So what is happening is that the upper sideband is 980 plus the plus FM. Our FM is 5 kilohertz. So you're getting the upper sideband is at 985. The lower sideband is 980 minus 5, which is 975. And the bandwidth is just in this case, the upper sideband minus the lower sideband. And that's 10 kilohertz, which would have been the same as 2 times 5. So the bandwidth, which is what we're having there. All right, that's just it. Total bandwidth of 10 kilohertz. The sidebands are so. What you are seeing there is if you had transmitted this thing on a carrier frequency that. Sorry, let me just read what I have there. A total bandwidth of 10 kilohertz. The sidebands from the first AM broadcast frequency extend down to 535. Yeah, I think this. I need to make a correction there because it looks like there are three things going on there. You needed to say that you have a transmission frequency of 1600 kilohertz, and so yeah. So ignore this part for now. I'll make the correction so that it reads better because what is being said there is the figures like 535 to 540. We were giving a range of the FM transmissions, and then there's an range for conventional AM. So it's sort of mixed up, and I think we can make sense out of this. Okay, so basically in the commercial transmission broadcast, you would have frequencies going from 535 to 1605. So that's what I'm capturing here. From 535 kilohertz to 1605 kilohertz. That's the commercial range. So in other words, if you had a radio, and radios are very rare these days, then the AM, the amplitude modulation band, the transmissions go from uh, 535 to 1605. But when you're tuning, you'll have one component at 540. So when you set the dial to read 540, then it is tuning from 535 to 545. And when you set it to 1600, it's tuning from 1595 to 1605. That's and it turns out that there are 107 channels, each 10 kilometers, 10 kilohertz wide. Okay, this I will write this better than what is showing there. It's not part of the example. It's basically a description of what is happening out there. Now, I had said I was going to stop. I'm trying to see where it's a good point to stop. Okay, maybe we'll stop here so that we can start next time with the reason for including the carrier. The reason for including the carrier is just so that we can use amplitude, the amplitude, um, this signal that is very easy to use, the envelope detector. I told you there's a circuit that uses just three components: a diode, a resistor, and a capacitor. A diode, a capacitor, and a resistor. This simple this simple circuit that is used as an envelope detector. We will study it um, at length. So I don't want to study it now because I'll not be able to finish. Uh, so if we include the carrier, then this thing can be used, and because of the simplicity of this, it is worthwhile to use this. But the other one, that double sideband suppressed carrier signal, will also talk about that to see what happens when the phase difference between the local carrier and the carrier that was used as the transmitter happens to be 90 degrees, then the signal will be lost. And that's the whatever the phenomenon that is called the quadrature null effect, not quadrature carrier, quadrature null effect of the coherent demodulator. Don't worry about the terms for now. So we'll pause. The next time we can continue from including the carrier. Now, this meeting is scheduled to be recurring, so it's supposed to go on every week from Monday. I have not done the one for the other class, and I'm wondering whether I should have it. I think what I'll do is I'll just give you some work to do, so we can be meeting once. I don't know how you're doing with the other classes. How are you doing it? Are you meeting twice a week?
Uh,
You
for
are.
some classes, we're meeting twice, but many
Uh-huh.
we're meeting once, and then the other class is used for tutorials.
Okay. So tutorials. How are the tutorials handled? You'll be given work to do on your own.
Uh, for some units, it's through the Google Classroom.
Yes.
So he sends some assignment, a short one, and then
Yeah.
we then scan and upload.
Ah.
Yes.
Maybe that's what I'll do. I think it's easier to get, because what is happening is that if we have to have a class as we're having now, I mean, then I'll be talking, and after some time you get saturated. And if we're
True.
doing it, twice a week, that way, I think it might be hard on you. But if after this, I can give you some work to do, then you'll be glancing back at these notes and perhaps playing back these sessions, and then you answer the questions. Then at least you won't be left behind. So yeah, we'll try that.
True.
Okay, so we'll pause there. I think there's some 15 minutes or so left, but I think it's good enough. Okay, thank you.